Unfortunately for our brave Kerbal-nauts, they were stranded around the sun with no power in their spacecraft. For our Dynamics and Controls project, we created a hypothetical situation, one in which a spacecraft is stranded in orbit around a sun without energy to get itself home. The system in our example is as follows. A spaceship orbiting the sun has no power left. However, they can use their solar panels on the top side of their spaceship to charge their craft and get home. In order to have the most efficient charge time possible, 3 angular-mounted photosensors are used on the spaceship to continuously monitor the spacecraft's orientation relative to the sun. The plant is used to adjust the orientation of the spacecraft so that the maximum amount of sunlight is directed at the spaceship as it orbits the sun. This is a continuous process because the system has to continuously check its orientation to maintain max efficiency. The coordinate frame is a body frame with the following axes orientations: X is pointing toward the sun, Y is pointing in the positive azimuthal velocity direction, and Z follows the right-hand rule off of these two. The governing equations for this system are similar to the last homework assignment equations, these being angular velocity and the quaternion. However, in this example, the quaternion does matter as the orientation is what we are trying to control. For our system, the input is the illumination data from the 3 angled photosensors used to triangulate the position of the sun, which is then converted to the angle measured off of the x-axis. Our output is the torque required to adjust the orientation of the spacecraft back to the desired position using a control moment gyro. The stimulus for the system is the light picked up by the photosensors and is therefore what is being directly measured by the system. This is then thrown into the negative feedback loop that creates a torque to fix the angle difference and then continuously rechecks the illumination for any further adjustments. Since we are trying to maximize the efficiency of our system, it is necessary to apply a measured amount of torque based on the error in our angle, and use a critically damped system to ensure we don't spend more energy than necessary to reach our target orientation. For this reason, a PID controller would be the most efficient. According to Wikipedia, a PID controller is a control loop feedback mechanism widely used in industrial control systems and a variety of other applications requiring continuously modulated control. A PID controller continuously calculates an error value as the difference between a desired set point and a measured process variable and applies a correction based on proportional, integral, and derivative terms, denoted P, I, and D respectively, which give the controller its name. The objective for our system is to keep our solar panels fixed on the sun while using the least amount of power possible. This is made harder by our spacecraft's continuously changing orientation with respect to the sun due to its non-circular orbit, as well as not having a stable position since the body frame itself is changing. The performance metrics used to verify if this is being done is the amount of energy used to keep the spacecraft not only at its desired orientation, but also from overshooting the same position. In summary, the system is a UFO orbiting the sun attempting to maximize charge via solar panels embedded on the top surface of the spacecraft. The governing equations for this are angular velocity and the quaternion. The system is continuous, with the inputs being the difference in orientation from the desired, and outputs being the torque to correct it. Illumination on the photosensors is what is being measured, and a critically damped negative feedback loop is being used. A PID controller is also being used for the system, whose performance metrics are the efficiency of the recharge. Finally, the coordinate system has X pointing towards the sun, Y in the positive azimuthal velocity direction, and Z following the right-hand rule.